Greetings, calculus students. This lecture will be about a rule of differentiation known as the chain rule. This first page is a review of compositions. Given two functions f and g, their composition or composite function is defined as follows. So you have one function referenced, f, a hollow circle, and then a second function, g of x. This notation means to take g of x and to plug it in for all of the inputs for the function f. And we read either of these two statements as f of g of x. Given the two functions below, find the indicated compositions. We have a function f and a function g. The first composition is f of g of x. This is where we take the rule for the function g, which is sine of x, and plug it in for these x's. So in notation, we would say f of g of x. G of x is the sine of x. And now we're going to, in particular, plug sine of x into the two different x's we see in the rule of f. So we have sine of x squared minus 2 times sine of x. This x and this x got changed to sine of x. So we could write this now without parentheses as sine squared of x minus 2 sine of x. The next composition is g of f of t. Focus first on this f of t. This is where we look to the f function here, and if I change this to t, then I change both x's to t's. So f of t is this same statement here, but t's instead of x's. Back to the composition. This composition means to do g of f of t. We know f of t is the same thing as t squared minus 2t. And now we need to take f of t and plug it in for all the x's in the rule of g. So this x right here, we will substitute t squared minus 2t in for that x. And so we get in the end the sine of parentheses, and the argument is t squared minus 2t. Now let's do a composition of a function with itself, f of a. This means to do f parentheses of f of a. Let's focus on what f of a is. If I change this x to a, then I change both these x's to a's. So we have f of, and then in parentheses, f of a will be a squared minus 2a. And now I want to take a squared minus 2a and plug that into f again. So once again, these two x's need to now be changed to a squared minus 2a. So we'd have a squared minus 2a, that's being squared, and then minus 2 times, and then once again, a squared minus 2a. Now we could take the time to multiply all this out and simplify, but we will not bother doing that in this video. Now find two functions f and g such that m is this function here, is equal to f of g. Give several possible answers. So we want to view this function rule as a composite function. There are many ways to do this. Basically, you can highlight any portion of this function, such as this radical of 3x minus 1, and think of that as the g of x. So one answer could be that g of x is square root of 3x minus 1. This would require f of x to be a certain result. The position that's currently highlighted in orange, you can just think of it as a position for an input, or just a simple x. If that were the case, f of x would be 2x plus 4. Now we can verify, if I do the composition f of g, we would take the g rule and plug it in for all the x's in the f rule, and that would give me 2 times the square root of 3x minus 1, and then after the fact, plus 4, which is exactly what the m of x function is. Here's a second way we could do this. Let g of x only be this 3x. This would require f of x to be, to substitute this orange position as a variable x, so f of x would be 2 times the square root of just x minus 1, and then plus a 4 outside of the radical. And sure enough, f of g would be, if you take this 3x and substitute it in where this x is, you would certainly get the m of x function again, which I won't bother rewriting. And here's a third way. Let g of x be everything inside the radical, not including the radical. G of x will just be 3x minus 1, no radical on it. Well, everything highlighted in orange just replace with an x instead. So you can see what the f function would need to be, and it would be 2 square root of x, and then plus 4. We could find infinitely many pairs of functions f and g such that m will be f of g. But the one way to do this that's going to be most helpful for us will be this third case. And the reason being is because this function we know how to differentiate, and this function we know how to differentiate. And that will be important in order to apply the chain rule, which we'll talk about on the next page. Moving on. Now to differentiate a function that is a composition, use the chain rule as shown below. So we have the differential operator, revealing that we should think of x as the independent variable, and we have a composition, f of g of x. I'll write the result of the chain rule without proving it, but to find this derivative, we would differentiate the f function. We call that the outer function, and then evaluate it again at g of x, And then we multiply this result by the derivative of g of x, also sometimes called the inner function. Now, because of this multiplication, and multiplication is commutative, it doesn't matter if you put the g of x here or if you put it in the front. Now, in other notations, here we have f of u. Notice this variable does not match this variable, so we assume that u represents some function of x. So to differentiate this, we would differentiate the outer function, plug in u again, and then multiply by the derivative of the inner function u prime. All right, let's apply this rule by finding two functions f and g such that y is equal to f of g of x. Then we're going to find the dy dx, the derivative of that composition. So here's our y function. X is the input variable, indicated by this x down here. Again, there are infinitely many ways to come up with an f and a g, such that f of g will equal this function. But the method that will be useful to us will be to think of what's inside the parentheses here as your g of x. So g of x, the inner function, is 2x plus 7. And then if you mentally change everything that's currently highlighted in orange to a simple x, this would reveal the f function. The outer function is x cubed. Sure enough, if you take 2x plus 7 and substitute it in for this x, you will get this y function we have here. These are good choices of f and g because they are individually differentiable using the rules that we've learned so far. Meaning we know how to find this derivative easily and we know how to find this derivative easily. So let's go ahead and do that next. So g prime of x will simply be a 2 and f prime of x would be a 3x squared. And now we're ready to apply the chain rule. So dy dx, the derivative of this composite function, will be, we do f prime of g of x. So I take the g of x function and I substitute it in for all the x's of f prime. So that would give me a 3 coefficient, and then the x I'm going to change and use parentheses to 2x plus 7, and then the exponent 2 outside the parentheses. This represents the f prime of g of x portion of our chain rule. And now we need to multiply what we have so far by g prime of x. G prime of x is just a 2, so we multiply by a simple 2 in this case. I can move that 2 to the front and multiply it to the coefficient that's there, the 3, and write this instead as 6 times 2x plus 7 squared. Now for terminology, whenever you have something raised to a power, this b is referred to as the base and the n as a power or an exponent. So taking a step back at what occurred here, we have a function y that has a base that's a non-constant function of x raised to a constant power. To differentiate this, that power 3 drop downs to the front. We repeat the base, and the new power is 1 less. But then we need one more step, and we need to multiply by the derivative of the base. This pattern will continue, and we can lean on it instead of every time figuring out what f and g are, and then their derivatives, and then applying the chain rule as you see it here. We'll discuss this on the next page. The chain rule can be used to create a rule for differentiating a function raised to a constant power, shown below. So we have the differential operator, revealing that we should think of x as the independent variable. Normally, any other letter you see here, you should think of as an unknown function of x, unless otherwise specified. And in this case, we are assuming that the power is constant. But the u is some function of x. Could even be a constant as well, but perhaps also a non-constant function. But the n, the power, must be a constant. If this is the case, then the derivative will produce, we do the power rule, where the n drops down to the front, we repeat the base, the new power is 1 less, and then we multiply by the derivative of that base. And this is our generalized power rule, which is just a consequence of applying the chain rule. Let's use this generalized power rule to find the following derivatives. So in the first case, x is the independent variable, which I see right there. But we certainly have a function, non-constant function, raised to a constant power 5. The generalized power rule says that 5 can drop to the front as a coefficient. We repeat the base, and the new power is 1 less than it used to be. And then one more step, multiply by the derivative of the base. So if this base we're calling u, then I need to put u prime right here. And the derivative of 7 minus 3x squared, the 7 goes to 0. And the derivative of negative 3x squared using the power rule again is negative 6x. Now this multiplication is important. If you make the dot too small or don't write it at all, be careful, this might look like subtraction. The safest thing to do really is to put your u prime in parentheses like this. However, I can now move that u prime up to the front and multiply it with the 5 and put all of that in the front. So we can write this now as negative 30x and then parentheses 7 minus 3x squared, and then that's being raised to the 4th. And here is our derivative using the generalized power rule. Now in this next case, z is the independent variable, so there's our z right there. I do see a function raised to a power 4. It's in a denominator, and then there's a constant 3 up here in the numerator. We'll want to rewrite this. We'll bring up the 6 plus z next to the 3, but with a negative 4 power. And of course, I have not yet differentiated, so I need to either put a ddz in front of this or just put a prime out here. Now we will use the generalized power rule. Of course, we have a constant here times this function. So using constant times function rule, we can effectively do this, ignore that constant, and just use the generalized power rule on what's inside the brackets now. So the 3 in the front will stay. Now use the power rule times negative 4. Be careful, again, about this notation. This could mistakenly look like you're doing 3 minus 4. So parentheses are a good clear way here. Then we repeat the base, 6 plus z. The new power drops 1 from negative 4 to negative 5. And then this 6 plus z's are u. We need to multiply everything by u prime. Well, z is the independent variable. The derivative of 6 is 0, and the derivative of z will just be 1. So this is a case where the chain rule does not have a noticeable effect because the derivative of the inside function is just 1, and multiplying by 1 doesn't change anything. But we can multiply the 3 and the negative 4, get negative 12, and then this negative power can move that 6 plus z back down to the denominator. So we get negative 12 in the numerator all over 6 plus z to the positive 5. All right, in our third case, y is the independent variable. I see a few different y's. I'm going to write this term as 5 times y to the negative 1. That will make my differentiation of that term easier when the time comes. And then this radical we'll write as a power 1/2. So I can write this instead as 3y minus 5y to the minus 1, all raised to the 1/2 power. Now I haven't yet differentiated, so I'll put this in brackets and put a prime sign, indicating that we still need to find the derivative. So the generalized power rule, the 1/2 will drop to become a coefficient. The base we keep the same. The new power drops 1 unit from 1/2 to negative 1/2. And this base is my u, so I need to multiply by its derivative, u prime. I'll use some parentheses for this. The derivative of 3y is just 3, and then the derivative of negative 5y to the minus 1, use the power rule on that. Negative 1 times negative 5 is positive 5, and then the new power goes from negative 1 down to negative 2. So all of this is my u prime. I'll simplify this a little bit, but not too much. I'll address this negative power by moving all of this down to the denominator with the 2. This term I'll keep up in the numerator. So our numerator is 3 plus 5y to the negative 2, all over a 2 times a 3y minus 5y to the minus 1 raised to the positive 1/2. And one step further, I'll get rid of the negative powers and change that 1/2 power to a radical. So this is 3 plus 5 over y squared, all over 2 times the square root of 3y minus 5 over y. And I recognize that this is a complex fraction, but I won't take the time to simplify this to become a non-complex fraction. We'll leave our derivative here at this stage. Now, as a shortcut for working with the square root of a function, recall that the derivative with respect to x of the square root of x winds up being, after a few steps, 1 over 2 square roots of x. This perhaps is worth memorizing to increase our speed of finding derivatives. Now, if I change that x to some unknown function u, the derivative of square root of u is the same. It's 1 over 2 square roots of u. If I take the rule above and change this x to u, then I change this x to u. But then the chain rule says to multiply now by the derivative of that inner function, so times u prime. This u prime and 1 can multiply, and you can put u prime in the numerator. So notice a shortcut in this case here. The derivative of the square root of this function, we put the derivative of the radicand in the numerator, and then all over 2 times the square root of that same function. This shortcut allows me to go from this step to this step rather quickly. All right, next page. Find the following derivative in 3 different ways. Notice that all 3 of these are the same. All right, in the first case, before I learned the chain rule and before I learned the product rule, we still had a way to find this derivative. We have a function raised to a constant power, but that power is 2, which means I can write the base twice and then FOIL them. So I'll do a little bit of prep work before I differentiate, which means I need to keep the ddx notation, or maybe just a prime notation. But we have 5x cubed plus 4 times the second 5x cubed plus 4. And now let's go through the FOIL process. So we'll have, again, the derivative with respect to x of 5x cubed times 5x cubed is 25x to the 6th. 5x cubed times 4 is positive 20x cubed. Again, 4 times 5x cubed is another 20x cubed. And then 4 times 4 gives me a 16. The 2 middle terms are similar so that I can combine them together, keep the ddx notation, and our function simplified is 25x to the 6th plus 40x cubed plus 16. And now this is a sum of 3 different functions, so I can differentiate one function at a time, which we say is differentiating term by term. And in each case, I just need the power rule. So the derivative of 25x to the 6th, 6 multiplies to 25, giving 150. X to the power drops from 6 to 5. Plus, power rule again, 3 times 40 is 120. Power drops from 3 to 2. And then the derivative of 16 is 0. Another way is to still write 5x cubed plus 4 twice like this. But instead of foiling them, we can use the product rule. because I have a product of two functions. Of course, they're identical functions, but we have a u and a v. So the derivative of this product will be u prime, so the derivative of 5x cubed plus 4, which is 15x squared plus 0. So here's my u prime. Then we multiply that by v, undifferentiated, times my v. Then we add to this u, undifferentiated, so 5x cubed plus 4. This is my u, and then times by v prime. And the derivative of v is also 15x squared. Now, of course, I'm going to distribute these 15x squares. 15 times 5 is 75. X squared times x cubed is x to the 5th. Plus 4 times 15 is 60, x squared. We're going to get the same two terms again, 75, x to the 5th plus 60 x squared. And we have two similar terms in orange and two similar terms in green. The orange ones combine to be 150 x to the 5th, and the green ones combine to be 120 x squared. And notice that matches what we got using the first method. But now that we've learned the generalized power rule, we can differentiate this a third way, because I have a function raised to a constant power. So that constant power will drop to be a coefficient. I'll repeat the function. The new power will drop from 2 to 1, and the base is my function u, and I need to multiply now by u prime. To use the chain rule, the derivative of u will be 15x squared. I can multiply the 2 and the 15x squared together now and write this as 30x squared times 5x cubed plus 4. The power is 1, so I don't need to write that. And now I can distribute. 30 times 5 is 150. X squared times x cubed is x to the 5th. And then 30 times 4 is 120. And then we have x squared. Again, getting the same answer that we've got before. As we learn more and more derivative rules, you will find that there are often multiple ways to differentiate a function, but they all yield the same result in the end. Okay, let's go to the next page. Find the following derivatives and simplify your results. These derivatives involve the same functions, but one is a product and the other is a quotient. In particular, this first one is a product of 3x and 2x plus 1 raised to the 8th. This is set up to use the product rule. Split right here, we have a function u and a function v. And the product rule gives us u prime v plus uv prime. So in this case, the derivative of u is the derivative of 3x, which is just 3, and then times v, undifferentiated, and then plus u, undifferentiated, which is 3x, and then times the derivative of v. V is a function to a constant power, so I used a generalized power rule just to get v prime. So that 8 will drop down as a coefficient, the 2x plus 1 will repeat, the new power will become 7. This base, I'll call it w, since u and v are already taken. Well, the chain rule suggests that we need w prime now to be multiplied to what we have here, and the derivative of 2x plus 1 is just 2. Now, I will multiply the 3x, the 8, and the 2 together, giving me 48x. So this first term I leave alone, plus 48x times 2x plus 1 to the 7th. Now the instructions say to simplify our results. This result can be factored. There are two terms, this term and this term, separated by the addition. Common to each term are some 2x plus 1s, and then maybe a 3 can be factored out of this 48 as well. So I'll factor a 3 outside these orange brackets, as well as the maximum number of 2x plus 1s, where there are 7 2x plus 1s in the second term and 8 of them in the first term. So I can factor out a total of 7. So we have 2x plus 1 to the 7th factored out. Now what would be left over in the orange brackets? Well, this 3's been factored out, and 7 of the 8 2x plus 1s have been factored out. So that leaves only a single copy of 2x plus 1 left in the first term. And then we have plus. We're going to factor the 3 back out of this 48. That leaves 16. The x is still there. We did not factor that out. But we did factor out all 7 of these 2x plus 1 factors. So that's entirely been removed. Now inside the brackets, I can simplify. And I'll just go back to parentheses. These parentheses here are no longer needed. And 2x and 16x can be added to make 18x. And then we have that plus 1. And here's my derivative in simplified factored form. Okay, same two functions, but we have a quotient now. We'll think of the numerator as u and the denominator as v. So applying the quotient rule, we would get u prime v minus uv prime all over v squared. So in this case, the derivative of u is just 3 times v undifferentiated minus u is 3x, and v prime, once again, I need to use the generalized power rule for this. So the 8 will drop down, the 2x plus 1 repeats, the new power is 7, and the chain rule, multiply this by 2, which is the derivative of 2x plus 1. And this is all over v squared. Well, v is already 2x plus 1 to the 8th, and then I need to square that. Okay, we're going to simplify a little bit in a very similar manner to what we just did with the product rule. This first term I'll leave alone for now. This 3x, 8, and 2 can multiply to, once again, 48x, and this is subtraction this time. Here, when you have a base to a power and you raise again to another power, the two powers multiply. So we would now have 16 as the exponent. Now think factoring of the numerator, put it in some brackets. Once again, we can factor out a 3 and 2x plus 1 to the 7th, leaving in the brackets a single 2x plus 1, which I don't need to put in parentheses, minus, and then a 16x, all over 2x plus 1 raised to the 16. Now that I've done factoring, I can simplify 2x plus 1 to the 7th over 2x plus 1 to the 16th, and I can combine 2x with negative 16x inside the orange brackets. Well, this power 16 is greater than this power 7, so we'll do 16 minus 7 to get 9, and all 9 of the remaining factors will be in the denominator. So I'll have a 3 times, and my orange brackets become parentheses. We'll have a 1 minus 14x, all over 2x plus 1 to the 9th. And this is our simplified result. Okay, move on to the last page. Find each of the derivatives below. Assume u and v are non-constant functions of the independent variable, and a and b are constants. So there are going to be a lot of letters here, and we change assumption based on what letter we're looking at. Let's look at this first case. The first thing to notice is what the independent variable is, which is x. So we have x to the 7 and u to the 7. X is the independent variable, but u and v we consider non-constant functions of the independent variable. So in other words, this u is some function of x. So I can differentiate term by term. Let's focus on x to the 7. Here I just use the power rule, and I get 7x to the 6th. I don't need to employ the chain rule here because the base is the independent variable. However, even if I do consider the base as some function u, and I want to use the chain rule, then I would need to multiply by u prime. But the derivative of x with respect to x is just 1. So you can even think of using the chain rule even when the base is simply the independent variable. And you still get the answer you would expect to get, which in this case is just 7x to the 6th. Now, as soon as I differentiate u to the 7, and u and x don't match, and we're assuming u is a function of x, then the chain rule is required. We'll use the generalized power rule specifically. The 7 will drop to the front. The unknown function u base is the same. The new power is 6. But then we need to multiply this by u prime, which I cannot say is 1 because I don't know what u is, and it doesn't match the independent variable x. All right, this example, independent variable is z. Remember, we're treating a as a constant, as specified here, and v is a non-constant function of the independent variable. Now, if a is a constant, then square root of a is a constant. So it should be that the derivative of square root of a will just be 0. And v we are assuming is a function of the independent variable z this time. Okay, so I know that the derivative of a constant ought to give me 0, and then minus. And I'll use my shortcut for the square root of a function. The derivative of square root of v will be 1 over 2 square roots of v, and then times the derivative of v. Now this v prime I cannot say is 0, nor can I say it's 1, because I don't know what v is. Furthermore, I can just put that v prime up in the numerator and write it this way. Now what if I had done this same thinking, but for the square root of a constant? That would have meant that the derivative of square root of a would be 1 over 2 square roots of a, and then chain rule times a prime, which I'll put in the numerator. However, if a is a constant, then a prime is 0. And then 0 divided by a non-zero number is just 0, confirming that if a is a constant, then so is square root of a, therefore its derivative ought to be 0. And now I can write this without the 0. The subtraction I can leave in front of the fraction or put it up with the v prime, which is what I'll do here. So negative v prime over 2 square roots of v. Okay, next example. W is the independent variable. U is a function of it. It's best to write this one in a different format. So we want to find the derivative with respect to w of 2u to the minus 6. And we use the generalized power rule because this letter and this letter don't match. And we're not assuming u is a constant. The negative 6 multiplies to the 2, giving me negative 12. The power drops on u from negative 6 to negative 7. And then the chain rule says multiply by the derivative of that base, u prime. And then, of course, I can rewrite this. The negative 12 and u prime can multiply together and be in the numerator. And that's a prime, not a 1 power. And then we have this over u to the 7. Okay, next example. X is the independent variable. I have a and b, which we are assuming are constants. And then v is the unknown function of x. So we have constant times the function rule and generalized power rule. So the b will drop down, multiply to the a. So my new coefficient will be a times b. The base v will repeat. The new power will be 1 less from b, so we say b minus 1. And then the chain rule requires us now to multiply by the derivative of the base, so times v prime. And I cannot say that this v prime is 0, because v is not a constant necessarily, nor can I say that v prime is 1, because v is not necessarily just x. We don't know what v prime is, because I don't know what v is. And we're done with this one. All right, this next case, y is the independent variable, and all I have here are a and b, but they're both constants. If we're assuming a and b are both constants, then so is a raised to the b. So we're really just differentiating a constant as far as y is concerned. So I do expect that this derivative will simply be 0. Or if I use the generalized power rule, I can confirm this. Since b is a constant, it would drop down as a coefficient. The base a would repeat. The new power on a would be 1 less. But then the chain rule would say that we need to multiply by the derivative of a. But this derivative of a, since a is a constant, is just a 0. And 0 times all this will just still be 0. So even if I use the generalized power rule, I confirm that I get 0. All right, and then our final example. We're assuming z is the independent variable. I see that z right here. However, this u is a function of z, and this a, this power, is a constant. So I do see that we have some sort of function raised to a constant. So I'll begin with the generalized power rule. The a will drop down as a coefficient. The u, z will repeat. The new power will be a minus 1. And this is my base. And right next to this, we need to put the derivative of the base. Or a base is a product. So the derivative of the base, we need to employ the product rule, which would be the derivative of the first factor, so u prime, and I cannot say that u prime is 0 or 1, because I don't know what u is, times the second factor, plus the first factor times the derivative of the second factor, z prime. However, z prime, because we're thinking of z as the independent variable, z prime is just 1, just like the derivative of x with respect to x is just 1. Well, the derivative of z with respect to z is just 1. So this z prime I don't need to write. I'll put a 1 here, but in my notes I'll remind myself that that was z prime. So in the end, I can write a times parentheses uz raised to the a minus 1 times u prime z plus u. Now this generalized power rule was the emphasis of this lecture, and it was a specific application of the more general chain rule. As we learn more derivatives moving forward, we're going to continue to see how the chain rule will be applied to more and more types of functions. So this lesson is really just the beginning of using the chain rule, which will be used extensively not only throughout this course, but throughout all calculus courses moving forward in mathematics. And this concludes our lecture.